Can you hear me? Okay. Thank you very much for the introduction. It was a pleasure to be here, and thank you very much for inviting us to this webinar. We had a great collaboration with DJI, and we will have the opportunity first to see what I-NERGY is about. Then Maria will talk about the synergies with DJI in more particular, and then we're going to see a very nice example by Sotiris of a service that we have developed. So artificial intelligence is bound to bring a revolution to the energy sector in various applications, including fast and accurate forecasts, demand and supply predictions, grid flexibility, optimized maintenance, and optimal operation. And these novel AI applications go beyond the competitiveness of the SMEs. They also hold the premise for a larger environmental and social impact. But it can lead to the decentralization, democratization, and digitalization of energy, which are crucial aspects, especially during the last years, as we've seen. So they can contribute to the sustainability of the environment, and they can help fight energy poverty as well as the climate crisis. So under this context, I-NERGY aims to build a framework for supporting the AI demand platform in the energy sector. The AI demand platform is the European one-stop shop for AI applications. I will talk more about it later. So I-NERGY will bring state-of-the-art AI and data technologies for enhancing AI demand platform. It covers all the spectrum of the electrical power and energy systems, starting from energy commodities networks, including transmission system operators, distribution system operators, as well as distributed energy resources and energy efficiency applications. So its objective is to reinforce the service layer of the AI demand platform, as well as to develop cutting-edge AI analytics and validate them through a number of pilot applications. The project started in the beginning of 2021. It has 3 years duration. We are 17 partners from 9 countries. 7 partners have experience in AI, ICT, and data in the energy sector. We have funding box to manage the cascade funding to startups and SMEs, and we have 9 electrical power and energy system stakeholders, covering, as I said before, the full energy value chain. So there's a good balance between the industry users and the technological partners, which is always a key ingredient for a successful AI project. This is an overview of our conceptual architecture, but later you will see more details in the next presentations. On the bottom, we have the data management services for the processing of the data. Thereafter, we have the AI models pipeline for taking this data and training the data and validating the models that are being created. These models are then deployed and further exploited by energy analytic services and applications used by the users. And on the top of that layer, we have the end users and the community from the AI on demand platform that we will utilize these services. The overall framework, as I said before, is implemented, demonstrated, and validated in real-life applications in 9 pilots, 15 use cases across 8 countries. We have a variety of pilot use cases, including the network assets predictive maintenance, loads and demand forecasting, energy demand prediction, energy saving verification service, consumption and flexibility prediction, as well as AI for the consumer comfort and preferences. We also have about the predictive maintenance for photovoltaic and predicting the demand for the electrical vehicles charging infrastructure. So you can give incentives for charging at a time where renewable energy sources are working or there are more energy efficient time slots. Peer-to-peer energy training in virtual energy community. AI for ambient assisted living and personal safety and security. AI for energy efficiency investments de-risking, as well as predicting how the climate change can have an impact on renewable energy sources such as the solar panels. All these pilots aim as an impact to decrease the energy consumption, to extend the asset's lifetime, to increase the energy efficiency, to increase the grid flexibility, the reduction of peak loads, the reduction of emissions, the reduction of operation and maintenance costs, the increase of the renewable energy sources contribution, reduction of the reverse power flow, as well as the power losses. We also organize two open calls to third parties. The first one ran between November 2021 and January 2022. It was addressed to SMEs and especially startups, and the idea was to create building blocks for new AI add-ons and services in the energy sector. This has been successfully complete, and the assets have been shared through the AI-on-Demand platform. The second open call was run recently between October and December 2023. And the idea here was to develop new service on the top of existing technologies, especially assets coming from the AI-on-Demand platform. The transfer program has already been, is currently running, the technology transfer program, and has 9 months of duration. So we have funded 15 projects there, and we expect to get the results by end of November 2023. So this is the assets of I-NERGY in a nutshell. On one hand, we have technical enablers such as the data management service, a common model, a complete MLOps pipeline for AI model training, evaluation, monitoring, and development, as well as a serving framework in order to serve these two trained models. And of course, we have the assets and services from the open calls that we have conducted. And we have the use cases from the pilots, as well as a number of services, including the energy load forecasting service, predictive service, and the rest that you have seen from the pilot, and as well as vertical services that can, horizontal service that can be reused to more than one pilot service. All these services in different form are being offered to the AI-on-Demand platform in order to be reusable by third parties. So in the form of, first of all, AI as a service, someone can use the APIs directly. In the form of code library notebooks, in the case where they're open source, as well as the whole application dashboard, documentation. We have also documented the use cases of the pilots, as well as you can find a number of datasets that someone can reuse in the platform. And these are shared in the current version, but also they will be shared in the future versions of AI-on-Demand that's coming soon, either as a catalog, in the catalog of AI-on-Demand, as well as the experiments, AI-on-Demand experiments. For those that don't know, AI-on-Demand experiments gives you a graphical interface in order for someone to be able to reuse a component made by another party and link it in a machine processable format through his own applications and run it on its own premises. So the technical enablers can be reused by other parties and domains. We have the AI service and models for the APS community. We have the industrial use case for the energy sector. We have managed to have beyond the state-of-the-art achievements, as you will see also in the presentation of Sotiris later. We have an early feedback of the industry users of what they need from AI-on-Demand platform and how this can be improved in the future. We put a lot of emphasis on the sustainability, meaning that the resources that are currently being used for the training are very trivial in comparison to the impact that the services have in terms of energy efficiency, as well as all the pilot users and the SMEs from the open call are going through an evaluation in terms of the ethics of the applications that are building by completing in a guided way the assessment list of for trustworthy AI that was created by the high-level expert group in Europe. So there are a lot of AI assets for the FS stakeholders and data scientists already on board on the AI-NERGY that someone can find and browse and see more information about each of these services. And in total, we have 26 AI case studies that will be soon be increased based on the results. And here you can see a few of the services that are currently on AI-NERGY experiment. Some of these services, you will be able to see them in the later presentations. So thank you very much. This is my presentation. I guess we'll have questions at the end of the webinar.
So, hello everyone, I'm Maria Borisov from engineering. I will be presenting I-NERGY project, precisely projects architecture and AGI collaboration. To implement all the services defined within the project, it was necessary to create a set of tools that would allow the development, testing, and execution of a series of ML models using mainly data from the various sources provided by the pilots. The main requirement was to have a cloud environment that would allow us to collect, model, and share data, as well as the ability to run our models, ML models, quickly, reliably, and efficiently. Finally, we needed a cloud platform that with tools and support that made it easy to manage the entire infrastructure. AGI was our choice based on previous positive experiences in other Horizon 2020 projects. The projects that the project partners had worked on, two of them being Matrix and EMSODEV. Through the AGI ACE call, it was therefore possible to have a dedicated project environment at the node provided to us by the Italian National Institute for Nuclear Physics, INFN-CNAF, Istituto Nazionale di Fisica Nucleare. The project architecture is based on specialized and interconnected layers. These layers will be schematically presented in detail in the following slides. As an introduction, from the bottom to the top, we can find the data service layer, which through the interoperability, harmonization, storage, and streaming modules makes it possible for us to collect, transform, and share data towards the AI trained model layer, where the model evaluation module allows us to manage the training and assessment of the quality of the models themselves, which are then served through the serving module towards the highest application layer, where the various services and digital twins have been implemented. The components identified in the various layers are managed in terms of security using tools provided by AGI relating to the configuration and management of roles and access rules to the project virtual machines, and by tools and services provided at the project level and implemented within the security framework. Looking a bit closer at the modules development, each of them, although deployed on different AGI virtual machines, is closely interconnected with one another. Different technologies have been adopted, and special configurations and implementations of them have been made. Data management services are based on Apache NiFi, which was appropriately configured as a cluster of 3 nodes to guarantee the stability and power of the platform itself. Also, within data governance, a storage environment based on MongoDB was created, and data streaming module based on Apache Kafka, also in a cluster, was implemented to guarantee the exchange of historical and near real-time data. Energy analytics services and applications. Applications for digital twins for distributed energy resources and for consumers and electrical and thermal communities have been created. Furthermore, all AI models for energy load and demand forecasting have been developed together with the data sets. Alongside these models, the load forecasting web application has been included. This application supports multiple functionalities for different roles and implements the entire ML pipeline. Additionally, advancements in flexibility forecasting and demand response services have been achieved. Moreover, other services have been integrated, the web applications have been developed, and data processing has been included, as well as ML models. Other services and platforms that are also part of the project are the Visual Analytics Engine and the I-NERGY Marketplace, as well as applications from open cause. AI Models Training Suite includes the Trained Model Store, Model Definition and Training, Cross-Stakeholder Transfer Learning, and Model and Serving Framework. Automated ML model storage is one of the main components. After training and evaluation, ML models are saved in the model store of the I-NERGY project. To accomplish this task, the MinIO is used. It works closely together with the MLflow to provide all the necessary means. The model definition and training components aims to exploit, assess, and implement different ML-DL algorithms and optimization techniques. The focus is on models relating to predictive maintenance use case. Regarding transfer learning, the implementation of user-friendly interface was developed. In the I-NERGY project, a well-rounded stack of technologies is selected to be used for the evaluation and serving framework. MLflow, MinIO, Anaconda, and Bank2ML platforms give a solid basis for all needed operations. As we already heard, everything in our architecture is strongly connected with the AI on-demand platform through I-NERGY assets, such as AI as a service, APIs, I-NERGY applications, datasets, ML models, Dockerized set of reusable I-NERGY models, datasets, microservices. The data service layer acts as a middle layer and gateway between the project data providers and the services, tools, digital twins, and modules developed in the context of the I-NERGY Analytics Service and application and AI Model Training Suite project layers. Data ingestion. The interoperability module is responsible for the management of the connectors developed to integrate inside the platform all the data coming from the different project data sources. The module can collect data in two ways: retrieve data and receive data based on the type of data source. Possible sources include SVTP, REST APIs, and databases such as MongoDB, MS SQL, etc. Data harmonization. Homogenization module, directly connected with the interoperability module, has been sharing the same environment and software core components. It has been in charge of data harmonization in terms of data pre-processing, such as data cleansing, anonymization, outlier suppression, and data formatting to a specific project's common data model and deontology to prepare data for the storing and streaming. Data storage represents the project database to store harmonized data to be available to all the project services and tools that will use them. MongoDB is used as a flexible and reliable database choice. Data streaming is in charge of stream ingested data to the I-NERGY Analytics Service and application and to the AI Models Training Suite layers. The data streaming is in near real time with low latency for the applications that need to process this type of data. Historical data are also streamed successfully. Models training, serving, and transfer learning tools. As far as the training, evaluation, and serving of ML models is concerned, several technologies widely used in the AI world and totally interconnected and complementary to each other have been used. Anaconda platform and its related tools have been utilized. Also, Jupyter Hub and Jupyter Lab with their configurable and shareable notebooks and working environments, MLflow for storing the various versions of ML models and their characteristics, and MinIO for storing models. Regarding the serving of models, a dedicated module has been implemented that is based on the technologies offered by BentML, all surrounded by the libraries and configurations useful for making the modules functional and performing. Energy analytics applications, digital twins, and AI services. As far as services are in question and digital twins, as we said, they were developed using the previously trained and evaluated models and then served via the serving module, making extensive use of the data made available by the I-NERGY governance system. Examples of such services will be better described and shown by my colleague Sotiris. Services and resources from AGIAs. Free cloud computing resources have been obtained from the AGIAs project for the development and deployment of the I-NERGY services and platforms. The software solutions have been installed on the official Project Cloud AGIAs environment. For some implementations, high-performance virtual machines have been employed, even with powerful GPU. Regarding storage, multiple volumes have been created and attached to the particular virtual machines. When it was needed, snapshots of the volumes and virtual machines were successfully created. Virtual machines and all related resources have proved to be reliable, highly available, and robust infrastructure for the I-NERGY project. These are the resources that are provided by the AGI for the I-NERGY project. They enable uninterrupted, solid, and easily maintainable cloud infrastructure for the project. The AGI infrastructure enabled a secure and reliable deployment and usage of all the I-NERGY platforms, services, and applications. So thank you very much. That's all.
So yeah, this is Sotiris Pelekis from ICCS, and I will be presenting the I-NERGY load forecasting service, or DeepTSF, which has been built and deployed to the AGI cloud, taking advantage of the benefits and high computing power provided by the platform. In this first slide, we can see a summary of the I-NERGY data-driven analytics services and application, which are the products of Work Package 4 of the project. I will give a brief overview of those services, as several of them are interconnected and interact with DeepTSF to produce their outputs. Amongst them, we have, of course, DeepTSF, which is the objective of this presentation. DeepTSF offers an API and web application that enables codeless machine learning operations in the time series forecasting domain, based on state-of-the-art deep learning models. Currently, DeepTSF is specialized to energy-related time series. Second, it's the digital twin for electrical energy communities that uses clustering techniques and DeepTSF forecast to optimize the electrical vehicle charging patterns within a network of charging stations alongside the commercial and residential prosumers in Greece. Then it's the digital twin for predictive maintenance that uses power flow simulation for predictive maintenance of lines and transformers within the power grid infrastructure in Portugal. This service uses active and reactive power forecasts from DeepTSF also. Then it's the energy efficiency investments de-risking service that aims to create virtual energy performance certificates and then propose renovation measures using as input a very limited amount of data on the buildings of interest. The flexibility forecasting and demand response service, which enables an AI-based consumption and flexibility prediction aimed for local community optimal aggregation and flexibility trading. In this service, clustering models alongside forecasts from DeepTSF are used to provide prosumer segmentation and incorporation into demand response programs. And finally, it's the visual analytics engine, which provides a visual dashboard for data related to electricity consumption centers such as electrical vehicle charging stations and buildings. Now let's proceed to our service. The question here is why DeepTSF? What was the motivation for this application in the project? And the answers were clear for us. First of all, keeping in mind the multiplicity of use cases that required forecasting in I-NERGY, there was a need for a holistic, automated, and extendable time series forecasting service that would be able to serve all of them together. Second, there was a need for mass execution of deep learning experiments through an automated and codeless framework for data scientists. That is for us to work easier. Third, it's the need for complex forecasting tasks such as multivariate and multiple time series forecasting, which are also supported by the tool. And finally, it was desired to offer the project's pilots the ability to monitor the high-level forecasting results and experiments. Proceeding to the architectural specifics of DeepTSF, the application is composed of 5 main subcomponents that are mainly deployed with Docker. First of all, the database. This is the project's MongoDB, mentioned also by Maria, that has been developed by engineering to host the pilot-provided datasets. DeepTSF receives harmonized time series data from it and subsequently feeds them to the forecasting pipelines. Then it's the forecasting backend, which is the core of DeepTSF. The DeepTSF backend implements a machine learning pipeline that enables data preprocessing, model training, including hyperparameter tuning, module evaluation, module storage and serving, and model logging. The key programming technologies used here are the Python APIs of MLflow, Darts, Optuna, and FastAPI. Also, model logging takes place within a dedicated deployment composed by MLflow, MinIO, and Postgres that we will see in the next slide. And the currently available models for forecasting are LightGBM, Random Forest, Temporal Fusion Transformers, LSTM, SEMPITs, Temporal Convolutional Networks, while more models are still under integration. What is important to mention here also is that the DeepTSF backend can be handled by experienced data scientists and machine learning engineers through a properly configured command line interface based on MLflow. Right after comes the identity and access management framework that ensures the authentication, authorization, and user role management. This framework is implemented with Keycloak in the project and is also used by DeepTSF. The next subcomponent, of course, is the workflow orchestration interface that is built on Dagster and enables the orchestration and scheduling of the workflows alongside error handling. I need to mention here, though, that this subcomponent is still under development. And the last one to be mentioned, but not least, of course, is the user interface of DeepTSF. The DeepTSF UI then allows high-level users such as energy experts and data analysts to have access to model evaluation results and automated model training. So let's take a closer look to the DeepTSF forecasting backend. As several services and technologies are involved there, it might have been a little fuzzy until now. This deployment mainly includes an MLflow tracking server, which is the UI for model logging, as well as the parameter and metric monitoring. The artifacts for the models are stored to MinIO buckets residing in the respective Docker container, while the parameters and metrics of the experiments are stored to a PostgreSQL container. The experiments can be triggered by the MLOps engineer from any machine, remote or local, as long as the rest of the services are accessible and the right credentials are provided. The MLflow command line interface enables this interaction of the engineer with the client, and also access to CSV files in the correct format or to the project's database is required to trigger a machine learning experiment. Moving on to the user interface, it provides a bunch of functionalities related to its different user roles. that are a model training menu meant for data scientists, a model visualization and evaluation interface meant for both for data scientists and energy experts who need to evaluate the developed forecasting models. And finally, a system administration, a user interface that gives access to the available resources of the VM, meaning a virtual machine, such as CPU, GPU, and memory usage. More details will be also demonstrated in the demo video that follows. This is the sign-in page of DeepTSF. Two main user roles have been created using the Keycloak security framework, namely a data scientist and an energy engineer. Aiming to demonstrate both of them, we're about to log in as data scientists, and as the functionalities of this role are a superset of the energy engineer role. DeepTSF is an AI service allowing data scientists to graphically trigger machine learning and deep learning pipelines for time series forecasting, while enabling energy engineers to visualize and inspect the results. The service has been developed using the React framework in the front end and MLflow and Fast API as the main components of the backend. A sidebar provides access to the various functionalities of the tool, which range from load forecast pipeline creation to experiment tracking and system monitoring. All of them are available to both energy engineers and data scientists, except for the first one, which is limited to data scientists as it requires modern skills. Let us first showcase this sophisticated functionality that allows the creation of forecasting machine learning pipelines in a graphical way, which is the log forecast. Here, the data scientists can upload a CSV file of their preference containing a time series. Then they can select a variety of parameters to define the training procedure. As we can see, they can resample the time series to a different resolution as a pre-processing step. And then they can define the train, validation, and test set split. After that, they can set the name of the experiment to be stored to MLflow, under which the specific pipeline will run. Then they can select the machine learning or deep learning algorithm, along with a desired set of hyperparameters. Those hyperparameters can be opted from a predefined list for now to ensure the feasibility of the execution. Finally, the forecast horizon can be set as it is necessary for the model evaluation process. The pipeline can then be triggered and the data scientist is prompted, as you will see in a while, to the MLflow tracking UI to inspect its progress and detailed results. So this is the MLflow UI. The ongoing and finished runs can be visualized here within the specific experiments. Additionally, there is access to hyperparameter values and the trained model per se, alongside evaluation matrix, plots, and other artifacts. These are the specific run, the metrics, artifacts here, which can be a plot of an evaluation plot, or the predictions of the model. Let us proceed now to the experiment tracking functionality of DeepTSF. This functionality is useful for energy engineers that need a quick overview of a specific experiment, as the first tab lets them fetch the best model that has been found within a specific experiment by evaluation metric. The user also needs to select the number of samples that they wish to include while visualizing the forecast. Then they get a summary of the evaluation metrics and the requested forecast versus reality plot that acts as a visual model evaluator. A second tab allows to examine the models of a specific experiment by entering the run ID of its respective evaluation stage as it is in MLflow. Finally, we also have here is how we copy the run ID and we get the results. And finally, the system monitoring tab, as we will see here, gives the users an overview of the application regarding the available resources in terms of CPU, GPU, and memory. Therefore, it allows them to monitor the workload at any time. A profile dashboard is also provided, including user data and available roles. In the end, the sign out button allows the user to exit the application. So that's it with the quick demo of the application. And To close this presentation, we would like to greatly thank the AGI project as we managed together to deploy DeepTSF and other services to a powerful virtual machine with an NVIDIA Tesla V100 GPU, 32 CPU cores, and 64 gigabytes of RAM, amongst other resources also offered by AGI. Given this very valuable asset, we utilized thousands of GPU hours that were spent on executing and forecasting experiments that include univariate load forecasting, multivariate load forecasting, and transfer learning use cases. And here at the end, I also include some references to papers that have been produced and have been accepted by international conferences and journals, thanks to the large-scale experiments that took place at the virtual machine offered by AGI. I would also like to mention that there are also other ongoing tasks and research on that that currently make use of the AGI resources. And therefore, in the near future, we hope for some continuation of this or a similar collaboration despite the end of the AGI project. Thank you. That's it from my side.